Morning, friends. So today, all of the assignment is going to be um, clearly independent. So you need to be able to manage your own time properly. Because if you're not moving through this quickly, you're going to get pretty lost. Because I'm not going to review this material more just because this part was remote. I believe that you're all on your way to going to college, and you all have to grow your ability to work independently. So today we're going to be talking about the heat equation. The things that we're going to be using today are this Edpuzzle video. Then the next thing that we're going to use after you finish this Edpuzzle video is the second Edpuzzle video that is attached in the Google Classroom. It'll have the other teacher's face in the top right corner. After you complete that one, then the third final thing that you'll do is this Google Doc. You'll be taking some notes during this Edpuzzle video on here, and at the bottom, you'll have some equations to work with. You're going to be working with this equation to answer some questions on here. Okay, let me go to present mode here. All these questions are just going to be paused for Edpuzzle, so reminder on what heat and temperature mean. So use these definitions up top to remind yourself of the do now. Which of these has more temperature? Why? And which of these has more heat and why? My hint is to count the molecules. Reviewing our answer, the right picture has more temperature. Remember, temperature means speed. Temperature means speed. It's not the same thing as heat. If you see the little arrows right here, little lines right here, we see that these little molecules are bouncing around faster. If they're moving faster, that means they have higher temperature. The right also has more heat because it has more temperature. Remember, heat depends on speed. Heat depends on speed, and it also depends on mass. So if we're saying, wait, but Murray, it also depends on mass, what about the mass? Each box has 13 of these red molecules. If each box has the same number of molecules, the mass has to be the same. That means the only thing that can change the heat has to be the speed of the molecules. That means it has to be the temperature of the molecules. It's the only thing that can change its heat. A reminder on these definitions, they're at the top of your Google Doc. Heat is energy that depends on mass and temperature. Increasing mass and temperature increases heat. Temperature is the measure of the speed of the molecules of matter. A reminder about this GIF shows us speed because these molecules are moving fast. That means that they have a higher temperature. Okay, so we also, as a reminder for how does mass affect temperature? Mass does not affect temperature. Mass affects heat. So the bucket here, because it has more mass, that means it has more heat. We see the little thermometer says, oh, both of these things are the same temperature. The bucket clearly has more mass than a drop of water, so it has more heat. For this class, what are we going to do today, this class? Because that was just a review from last class material. So this class, heat versus temperature. We know that they're different, but why do we care? Then we go on to how do we measure temperature? Then we go on to how do we measure heat? How do we measure heat? And we're going to see that this equation is going to be pretty helpful for us today. Q equals mc delta T. Review of the exit ticket from last class. Describe how the temperature inside a teapot would change if all the molecules slowed down. Keywords here, slowed down. That means the speed is going to decrease, temperature is going to decrease. Number 2, describe how to change the heat without changing its temperature. Well, heat depends on mass and temperature, so we have to change the mass. If you want to decrease the heat, you have to decrease the mass. If you want to increase the heat, you have to increase the mass. A reminder to use your definitions. Use your definitions. Here's a little ranking. I want you to give me a ranking here. Which one of these is the best? Which one of these is the medium? Which one of these is the worst? My own personal ranking here, definitely shrimp number 1. I think chicken gonna be at number 2, and I'm sorry, folks. I'm not the biggest fan of steak. I'm putting that at number 3. Okay, so we're gonna talk about cooking here because I want you to walk away with chemistry from something that you're going to use every single day. Something that, like, you got to say, Murray, wait, oh, chemistry actually is helpful. Chemistry is going to actually teach me something that I need to use. Because say that you're cooking some amount of meat or some amount of vegetables, it's going to work the same way for vegetables as it is for meat. You're going to have some options in the kitchen. I'm sure you've seen your parents or somebody around you, or maybe you work in a kitchen, you see different types of frying pans get used. You can think about copper frying pans, aluminum, stainless steel, and iron. Those are like our types of frying pans that we see right here. And depending on what type of frying pan you use, you're going to get, you could get great results, you could get okay results, or you could get bad results. And depending on what type of frying pan you use, we're gonna think about this. Um, okay, prediction. Which of these two pans do you think is better? Because depending on which pan you use, you might end up with like beautiful golden crispy chicken, or you might end up with straight charred mess, a straight charred mess. So, if we want to break this down in terms of something that we've used to think about um, in chemistry, when we talk about inputs and outputs of this system. So, the system is in the middle. The system is in the middle. The system is our cast iron frying pan, our cast iron frying pan. And we see some images to the left and we see some images to the right. We see some thermometers here. Make a prediction. What are the inputs and outputs of this system? What are the inputs and what are the outputs? The inputs and outputs that I was going for are it's not necessarily, we're not putting in temperature into the system. What we are putting into the system is heat energy. Energy is the thing that flows into systems. Temperature is not the thing that flows into systems. When we put the energy into the system, the result or the result is that the cast iron pan is going to increase in temperature. The result of putting heat into the pan is a temperature increase. An important thing to note is, well, you might say, like, well, Murray, if the temperature of the pan increased, doesn't that mean the heat energy of the pan also increased? Yes, you would be right. So you could say temperature increase here. You could also say heat increase here. But I'm going to say temperature increase because I want to be specific about what is increasing. Because if you said heat increase, I was like, okay, well, did the mass increase? And no, the heat going into the pan did not change the mass of the pan. It didn't change how much pan is there. It only changed how fast the molecules of the pan are moving. All these iron molecules are now vibrating faster because they're hotter. Okay, so we got another prediction here. What is the same and what is different about these two systems? You got one system up top and one system down below. So, something to be clear here, energy input is the same for both pans. Like we're using the same burner for both of these pans. We're going to use like a medium burner for both of these pans. And what we see here is for the iron pan, we see a small temperature increase, but for the aluminum pan, we see a huge temperature increase. So we ask ourselves, wait, hold on, Murray, same amount of heat in, how come the temperature is changing differently for these two pans? And maybe some of you who've been in the kitchen have experienced this. If you've used an aluminum pan before, you might notice that those get hot really quickly. But for a cast iron pan, those don't get hot really quickly. Those take a little bit more time to heat up. And maybe you've also experienced that. If you cook with a cast iron, you maybe have gotten some beautiful crispy golden chicken, and you've cooked with aluminum pan, you might have burnt your food. You might have burnt your food. We're going to think about this with a new framing here in terms of system and surroundings. The system is going to stay the same here. The system is our cast iron pan. And we're going to talk about the surroundings in green. Everything that's not part of the system, this helps us show where the boundary of the system is. Because everything that's on the outside of the pan is part of the surroundings. It's outside of the boundary of the pan. In this case, we're thinking about the burner that the pan might sit on, might go on top of this. The heat is going to flow into this system. The heat flows into the system. Our goal is for us to pass the heat of the pan to the chicken. So we have heat flow into the system from the burner. We have it go to the pan, and then we have the heat flow out of the system and into the chicken, or the steak, or the shrimp, or the vegetables, whatever you're really trying to cook. No matter what, you're probably going to be using a pan to cook something at some point in your life. So it's probably important to understand, well, how does the food cook? In order to understand how the food cooks, we need to understand how do we measure heat. We can measure length, which is something that everybody can measure, right? You might say, how tall are you? And you might tell me the number of feet in inches. Or you might say, how many miles from school are you? And you might be able to tell me the length, the distance between you and school. Those are all units of length when you measure that. And you've talked about temperature before. You might say, like, how hot is it outside today? And you might say 60 degrees. But it's important to note that when you're talking about those temperatures, oftentimes you're talking about temperatures in Fahrenheit. In this class, we're not going to be talking about temperatures in Fahrenheit. We're going to be talking about temperatures in Celsius. Just like Europeans and almost everywhere else in the world uses, we're going to be using Celsius. Why? Because the math is a lot easier to do with Celsius than it is with Fahrenheit. Just makes sense. Scientists love using Celsius, and we'll see why. So you would say, okay, temperature, yeah, measured in degrees. Yep, that makes sense. And the last thing here, this is new. We measure heat in joules. This is pronounced joules. So try saying that to yourself, just like a necklace. This is pronounced joules. So if you come to this in class, be like, joules? No, joules. So, okay, length measured in these types of things, inches, feet, meters, miles. There's more measurements than that. Temperature is measured in degrees. Heat is measured in joules. So if you told me, okay, Murray, how hot is it outside? What's the temperature outside? And I said, it's 30 feet. You'd be like, Murray, that doesn't make any sense. You just gave me a unit of length. You need to give me a unit of temperature. I'm like, oh, yeah, sorry. 30 degrees Celsius. Okay, that actually makes sense. And if I said, yo, how much heat is in that frying pan? If you told me, oh, the frying pan is 50 degrees, I would be like, what? What do you mean it's 50 degrees? That doesn't tell me how much heat there is. That's like saying you are 50 degrees tall. That doesn't make any sense. Heat is a unit of joule. All energy is measured in units of joules. And we're going to practice that if that doesn't make quite sense yet. And what we're going to practice is this new equation called the heat equation. This is a new equation that's going to relate four different variables. We have Q, that's one variable, M, that's another variable, C, that's our third variable, and our fourth variable is delta T. It's the triangle and the T next to each other. That is just one variable right there. Q means heat. Why does Q mean heat? Probably because this is derived from a French equation, and Q probably was a word that related to heat at the time that it was made. M means mass. Okay, thank God. That one's a little bit easier, right? C means specific heat, and I'll get to that in a second. You're gonna say specific heat, like Murray, what you talking about? Delta T means change in temperature. It's really important that we got the change in temperature. Remember, in algebra, you might be talking about delta x to mean change in x, delta y to mean change in y. You can't just use one value of temperature. You need to use the change in temperature, or you need to be looking for words in an equation that indicate that I'm giving you a change in temperature. Specific heat, getting more into specific heat. Specific heat is specific to each substance. Like water is a substance. Water has some value for C, but that's not going to be the same value as for iron, which is a different substance. It's not going to be the same as for coffee, which is a different substance. It's not going to be the same for bricks or for aluminum. Each substance has a different specific heat value. The next Ed puzzle video is going to get a little bit more into specific heat. But for right now, you just need to know that you need to plug it into the equation. It's an also important note that I'm always either going to give you this value of C, or you'll have to use algebra to isolate it, get it by itself in the equation, and then solve for it. You'll always have the other three if you're trying to solve for one of them. So folks, you're going to copy these into your Google Doc. There's a spot at the top in your Google Doc right now. So you're going to pause and you are going to copy these variables, the definitions, and the units. The reminder, the units here. So heat is not measured in degrees Celsius. Temperature is measured in degrees Celsius. So change in temperature is also measured in Celsius. Heat is measured in joules. Remember that word joules? So that's abbreviated with a capital J. Mass, in this class, we're going to measure in grams. You could also measure it in kilograms, which would be kg. That'd be just be 1,000 times grams. But in this class, we're just going to use in grams. And specific heat is a combination of all three of the variables. Look at that. That's kind of interesting, right? So the specific heat has something to do with the amount of joules, the amount of energy, divided by, which means per, the grams times the degrees Celsius. So it's got something to do with the amount of energy per the amount of mass times temperature. Interesting. So make sure you get those in your notes. On this heat equation, Q, that means heat. T, that means temperature. Don't forget the delta, that means change in temperature. If you're plugging in just one value of temperature from a word problem, you better be sure that value is a change in temperature. I got to use some words to indicate that it's a change in temperature. I might say, this coffee decreased by 40 degrees. If I said it decreased by 40 degrees, that would indicate a delta T. If I said this coffee is 40 degrees, then you would say, well, Murray, okay, it is 40 degrees, but what is it going to? What's the change in temperature? A reminder, heat means energy. Q means energy. Q means heat. T is the speed of the molecules. Temperature means speed of molecules. Let's do an example here. Calculate the heat exchanged when a 100-gram glass of water increases temperature by 100 degrees Celsius. I'm giving you here, increases the temperature. Okay, it sounds like a delta T to me. The specific heat of water is 4.18 joules per gram Celsius. So we have to ask ourselves, what are the variables that we're given? M is the mass. Okay, so mass, I remember if you look back at your notes, what are the units of mass? Grams are the units of mass. So if you look for the number with a G, you'd say, oh yeah, that's right, that's our mass. Delta T, okay, that's usually the one with just the amount of temperature. So that's a degree C right there. And specific heat is the one that's got all of the units in it. So it's got joules, grams, and Celsius. Joules divided by grams Celsius. What do we want to measure? So if we got three of the variables, we must be looking for the fourth one. Let's look at the equation up here. Q, M, C, delta T. We have M, delta T, and C. We've got all of these ones on the right. That means that we need the one on the left, Q. Ooh, that should be an easy one for us because when the letters are next to each other, when the variables are next to each other, that means we have to multiply. So what is heat here? So I'm going to pause the video for you to give a shot at this. Remember that you've got the equation, you have the values for each of the variables. Now you just need to solve for Q. So in order to plug this into the equation, what we have to do is simple. For this type of setup of a problem, it's simple. We don't know what Q is, and that's on the left of the equation. Everything else is simply plugging it in. M is 100 G, C is 4.18 joules per gram Celsius, delta T, because I gave you an increase in temperature right here, that is 100 degrees Celsius. When you multiply all those numbers together, you get 41,800 J. Make sure you don't forget the units. J means joules. Joules measure how much heat. It tells me how much energy there is. If you just say 41,800, I'd be like, 41,800 what? Cockroaches? Backpacks? Eiffel Towers? Like, bro, what are you talking about? And you'll find out more and more over time that including what you are talking about will save you time because you'll be at a job one day and you're going to tell your coworker, "Hey, can you grab 5?" And they'll be like, "5 of what?" And they're going to and it'll save you time if you just say, "Oh, 5 coffee cups." Like that's what I wanted. That's the unit of what you're talking about. It's important to include the units so that other people just understand what you were talking about. On the Google Doc for today, I'm going to be asking you for answers in context. What do I mean by that? I mean that you answer in a complete sentence and you talk about the substance that is involved in the problem. In this problem, we are talking about a 100-gram glass of what? Of water. That is the context of this problem. So the answer in context is this means that we gave 41,800 joules of energy to the glass of water. That is our answer in context. What does it look like in context? Because just using an equation alone, like Murray, why do I care? The surroundings are giving heat to the water. Heat is flowing in, say from possibly from a stove, could be from a microwave, multiple different ways to have the heat flow in. And the value of the heat that flows in is 41,800 joules. The output or is the response in this system. It's that water's temperature is going to increase by 100 degrees Celsius. Let's look back at that equation. Q equals mc delta T. We have related Q, the input to the system. Q is the input to the system. It's the amount of heat. And the response was the delta T. So we flow in this much heat into the system, and we have the system respond by having the water increase by 100 degrees Celsius. Okay, so you are going to try this problem on your own. I'm not going to read it. You've got eyes. I know you can read it yourself. So pause and try this on your own. So this problem looks like this. So I look for, again, mass. I'm looking for the G. G means grams. That means how much of something. The mass. The change in temperature here. So, oh, it says increases temperature. Okay. Murray's words have indicated that this is a delta T. So we got 10 degrees. Specific heat is different. Notice this is a different number. Why? Because iron is not the same as water. So it's a really similar setup where we plug in the three numbers. We plug in m, c, delta t. They multiply by each other, and we get a different value here. A different amount of heat has to go into the iron. Iron is a different substance, so it's got a different specific heat. We change it by a different temperature, and there's a different amount of it. Of course, the value of energy is going to be different. What does this look like? Well, a cast iron pan is made of iron, so the specific heat of a cast iron pan is going to be the value that we're talking about. We could be talking about heat flowing into this cast iron pan, this much energy, 5,280 joules, and the response of the pan is that it increases by 10 degrees Celsius. Here's a little bit of a break. Here are 3 practice questions. So you're going to pause and you're going to practice these 3 questions, and I'm going to review those answers here. So the first question was all about was just as simple as the ones we were doing before. We were plugging in the 3 values, and you get this is the value for Q. Delta T is the final temperature minus the initial temperature. So in this problem, we are talking about wanting to raise a steak's temperature from 4 degrees to 60. You wanted to go from 4 to 60. You'd say, what is the change in temperature? What is delta T? What is the change in temperature? The change in temperature is 60 minus 4, because that's the ending temperature minus the starting temperature. then you can use that delta t in the problem below, and then it's plugging it in again in your area. This is your value of energy. What you are doing next, folks, what you're doing next. What you're doing next is the Ed puzzle that's attached to the Google Classroom assignment. And then you are scrolling down to the bottom of this and working on these practice problems. You may work with a friend on these practice problems. I'm totally fine with that. Um, if you, and I want to highlight this, super important, if you want more equation practice, like that's why this YouTube video exists right here. If you need extra practice before you move on to what's below, that's why this YouTube video exists. Okay. That's the front part of class. If you're like, Murray, that took a really long time. It probably took less than a regular class's length, so no complaining. Um, I will see you all again, I guess, a little over a week. Bye, friends.